In today's video, we will see different types of transformer winding connection or the grounding system, and what is the impact of the transformer winding connection in three-phase short circuit or unbalanced faults like single line to ground fault, line to line fault, or double line to ground fault. Mainly three-phase faults and balanced three-phase faults and single line to ground fault and line to line faults. So as you can see this, I have drawn one simple network here. This is 33 kV, grid is 33 kV, and here is the grid parameters: 40 kiloampere short circuit current, X by R ratio is 14, 33 kV bar 6.6 kV transformer is there. This is a 10 MVA transformer I have connected and taken the typical impedance and X by R values. One more thing, the grounding connection. This is delta star grounded, delta star solidly grounded, DYN1 vector group. We are not interested about this vector group today, but we will be talking about this winding connection. This is delta star solidly grounded system. So let's run quickly. Let's run the IC 60909. Okay, three phase faults. So here the short circuit current is 10.945 kiloampere, 10.945 kiloampere. And just to compare this result, let's create some more case studies. Like this is delta star solidly grounded. Let's say this grounding connection is star solidly grounded and star solidly grounded. You can see the vector group is changed, not vector, yeah, vector group is changed, and also the winding connection. Let's take another case. Keeping the same secondary side, same solidly grounded. Let's say this is star, but this is ungrounded system. This is ungrounded. So okay, so I have created three cases. The only difference is that all other parameters are kept same. Only change is the transformer winding connection. Here it is delta star solidly grounded. Here it is star solidly grounded system. And here it is star ungrounded system and star ground solidly grounded system. So this is the only change. Now we will create the fault here. So firstly, let's check the three-phase fault, three-phase short circuit current. What will be the impact? For three-phase short circuit current, what will be the impact of transformer winding connection? Can you guess? As you can recall, this I have already prepared that short circuit for this short circuit case. I have already prepared, that previous videos how to calculate manually, how to calculate short circuit currents manually, three-phase short circuit current, single line to ground fault short circuit currents. So how to calculate manually and validate using ETAP software. If you have not watched till now, you can visit that. You can visit those 3-4 videos. Then it will be very much clear how the three-phase short circuit currents are calculated, how unbalanced currents using asymmetrical, using that symmetrical components, positive positive sequence network, negative sequence network, zero sequence networks, how to calculate the three-phase short circuit currents and unbalanced fault currents. So everything will be cleared if you watched, if you can watch those videos. Okay, so as per the calculation method, the three-phase short circuit current is V by Z1, means positive sequence impedance. So this positive sequence impedance Z1 does not depend on the transformer winding connections. The positive sequence impedance does not depend on the transformer winding connections. So only the transformer winding connection will have an impact in the zero sequence component of the network. Once again, only the zero sequence impedance Z0 will be impacted by the transformer winding configurations. So that is why any ground fault, it may be single line to ground fault, it may be double line to ground fault. So in those cases, the short circuit result will be different as your transformer winding connection is getting changed. Otherwise, in case of three phase or balanced short circuit current, means in case of three phase short circuit for fault current, there will be no change. In case of line to line short circuit current, there will be no change, because for line to line short circuit current, Z1 and Z2 means positive sequence impedance and negative sequence impedance are responsible, but not the Z0 zero sequence impedance. So for three phase short circuit current or for line to line short circuit current, there is no impact of the transformer winding connection. Only impact is for the ground fault, means single line to ground fault or double line to ground fault. So now let's simulate this. What will happen? We'll see the three phase short circuit current. Sorry, I have run this device duty. No, I will run this IC 60909 just to show also the single line to ground fault and line to line fault also. Okay, that's fine. I have run this. As you can see, this is three phase fault, three phase short circuit current. So in all the cases, short circuit current values are same: 10.945, 10.945, 10.945 kiloampere. Because as I explained already, this three phase short circuit current depends on positive sequence impedance Z1, and this transformer winding connection does not have any impact on Z1 or Z2. Now let's take the single line to ground fault current. What will happen? What will happen? Definitely the values will be changed. Now you can see for this single line to ground fault current for delta star connected transformer, it is coming single line to ground fault current is 11.148 kiloampere. Whereas for star connected solidly grounded transformer winding, the fault current is reduced. It is 10.945 kiloampere. Why? You should ask the question why. For this delta star connected transformer, for this delta star grounded transformer, the zero sequence current cannot flow towards the primary side. Means since the primary side of the transformer is delta connected, there will be no zero sequence current flowing, and there is no contribution from the grid. That means grid impedance is omitted. There is no, in this short circuit current calculation, grid impedance, source impedance is not considered. So that's why impedance is less, source impedance is not there, only the zero sequence impedance reflected by this transformer winding connection, only this impedance is there. So that is why the fault current is more. If you want to understand how the zero sequence, positive sequence or negative sequence network will be drawn, how to draw that, so I can make separate videos, or you can go through some of the some of the basic books, or you can search in the internet also. how the equivalent symmetrical component networks will come. So from that network it will be clear. Because this is delta star grounded transformer, the grid impedance will not be there, right? So the overall impedance, the zero sequence impedance is less, and fault current, single line to ground fault current equals to 3V divided by Z1 plus Z2 plus Z0. Since Z1 and Z2 remains same, there is no change in Z1 and Z2 value, but definitely there is a change in Z0, because in the Z0 this grid impedance is not there. Whereas for this star grounded, solidly grounded transformer, here you can see this is a star grounded. So if you draw the equivalent impedance network for this system, then it will be cleared. So there the grid impedance plays an important role, means this grid impedance is also added with this transformer. So the overall equivalent impedance will be seen by, that's grid plus this transformer. So in that case the short circuit current will be less. So it is coming as 10.945. How it is coming? Because considering that calculation, manual calculation, and as per the manual calculation also, you can see, you can watch the videos. I have already prepared that video in detail, so everything is there, that manual calculation starting from the grid, the transformer, how to find out the R and X values, how to do that, how to consider the C factor, how to consider that series connection, parallel connection. So everything in detail, that video, those videos will help a lot, though those videos are lengthy, but you need to keep patience to learn something new, because this is nothing new, but sometimes we struggle to validate our manual calculation with the ETAP generated or any other simulation software generated output, because of some of the factors, means that C factor, what ETAP is considering the C factor. What you can see here, the C factor is 1.1, but in our manual calculation we are not considering this C factor as 1.1. That's why the result may not match. What else? What else? What else? That in our manual calculation, generally we consider the Z values, the impedance value directly. We are adding Z1, this Z value of grid and Z value of transformer, but that should not be like that. We need to split into R value separately, X value separately, and we should add this R value of the grid with this R value of this transformer, the X values of this grid with the X values of this transformer. And again, before adding that, we need to ensure that in all the cases the base MVA should remain same. Means on the common base MVA we need to calculate, means we need to add this R value and X value, otherwise it will be wrong, it will not match with the ETAP software. So these are the parameters I have explained in detail, and I have shown how to calculate manually and how to validate using ETAP software. You can watch those videos. Okay, now coming to the third option. Here you can see this is the primary side is star connected but unearthed system, and secondary side is same, means solidly star grounded system. So here the single line to ground fault is 0. Single line to ground fault is 0 kiloampere. Why? Because there is no zero sequence there is no zero sequence current circulation path here, because in primary side it is star connected. It's not delta. If it is delta, now you can see, you may ask this question. Here it was delta star grounded, and here it is star ungrounded. So in both the cases those are ungrounded system only. So where is the difference? The difference is, if we see the line to line current, here you will see the line to line current, it is 9.479 kiloampere. Okay, 9.479 kilometer. That means zero sequence current is already flowing actually inside that transformer primary winding, delta winding, right? So whenever you are creating single line to ground fault, whenever you are creating single line to ground fault, that time in primary side, there is no ground current. Okay, that is fine, but there is a this single line to ground fault will be reflected as line to line fault here. Will be reflected in the primary side line to line fault here. But in this case, since the primary side is ungrounded, here there is no path for the zero sequence current flowing inside that winding also, and that's why though the transformer primary side is solidly star grounded, there will be no single line to ground fault current here. Okay, so what we have discussed in case of three-phase short circuit fault, just to recap, in case of three-phase short circuit fault, there is no impact. There is no impact in the three-phase short circuit current. There is no impact of the different winding connections. But in case of single line to ground fault, definitely there is impact because of the zero sequence impedance, because of the zero sequence current, and it will be different for a delta star grounded transformer, different for star grounded system, different for star ungrounded and star grounded system, that will be different. So for this system, it is very challenging. For this star ungrounded system and star solidly grounded system, it is very challenging. If there is any fault, single line to ground fault, the system will not be able to detect any ground fault. The relay, if you connect also the relay, it will not be able to detect that fault. That's why there should not be any single phase load in this level 6.6 kV, or it may be or it may be 415 volt also. If it is 415 volt LV bus, if it is LV bus, then also we should not add any single phase fault. Yeah, sorry, any single phase load here. Okay. Generally, we do not recommend this star ungrounded and star grounded system. Most of the cases you will see delta star grounded system, right? So up to this, in this video, I have discussed the impact of different transformer winding connections on different kinds of short circuit currents. If you want to know more in detail, let me know. I can prepare more detailed video also. Okay, thanks for watching this video.